Hello, hello.
Somebody's laptop. Why did you use it? Huh? No, no, no. Fine. I'm not doing that. ओके, ड्राफ्ट हो गया उसका, उनको लंच के टाइम घर जाके भेज देंगे. डोंट वरी अबाउट इट. ओके, so the next issue that we want to talk about is the group specific trend, right? So the way we want to think of that, note, I can have some, basically something like a group following a particular trend. So if you belong to this income quartile, you will follow one trend. If you belong to the other, you will follow another trend. If you belong to another, you will follow another trend. Clear? And the way I want to then think of my cross-sectional effect, alpha S, my time effect, gamma T, then I have the tau st, that's my group specific effect, and I want to multiply the group specific effect, allowing for something like a different trend. Clear? So the way I want to think of, I can complicate this model even further by multiplying tau with my tau st. So no, tau st is nothing but an intercept. If I do something like the multiplying the lambda or the dst with my tau, I get something like this group is having here and then with a different slope. This group having here but with a different slope like this. This group is having here but with a different slope like this. But if I don't have the trend, I will have just the group specific intercept and they could differ. Okay. Then what I want to think of, that tau st in my notation is nothing but a group specific dummy multiplying by the time trend. So yeah, fine. So I have already tau st, the notation captures what I was trying to think of. T times, actually you can think of T times the group specific dummies. Okay. So the way I then want to think of that there could be some nonlinear trend, right? Recall my diagram. One is this, one is this, one is this, one could be this. I do not know them, right? And I want to capture that. The group specific time trend in outcome means what? That the treatment and the control groups, they follow two different trends, which is quite possible scenario, right? I do not have to have the same trend for the control as well as for the treatment. It makes DID estimate more robust. When does it make it more robust? When the pre-treatment data establish a clear trend that can be extrapolated into the post-treatment period. Remember, I want to break away that they follow the same trend. So what I want to do, The pre-treatment period, I want to analyze their trend. Once I analyze their trend, I want to think of that trend, I want to superimpose on my post-treatment period. And I want to do that simply because I claim that that would make my DID lot more robust, given there is a change in the trend. Okay. In one way you can think about, Besley and Burgess QJE is one way to think about they did that. So what is the basic idea of the paper? They want to think of that labor regulation on business in Indian states. Why? Because different state has different type of labor regulation. Okay, and method was difference in difference. The data is states in India. Dependent variable was log manufacturing output per capita at the state level, and then independent variable is labor regulation, but they have used lagged labor regulation, right? And they have coded it. How they have coded it? That pro worker, neutral, and the pro employer, where West Bengal, of course, was pro worker. Some state was zero, neutral, and some state was anti worker or something like pro employer. And then they accumulated over the period to generate something like a labor regulation measure. So, but here they have allowed for different type of trends, right, or group specific trend, because why? Pro labor state can follow a trend which is different from the neutral state, which is different from the pro employer state, right? So three groups, three different trends we can assume. Yes.
Labor regulation was also introduced in different years.
Labor regulation is a measure that they have done it in terms of the whatever the changes has happened during their sample period, they create the labor regulation measure, keeping that dummy as 1, pro worker 0, and then -1 as pro employer. Okay, fine. I'm now going to move into triple differencing. I'm going to go back to bring my card papers example. Recall Pennsylvania and New Jersey. So more convincing analysis sometimes comes from higher order contrasts. And one of the higher order contrast we can think of is in terms of triple differencing. Okay, so it would be difference in difference in difference rather than difference in difference. So one more difference with a hyphen. Clear? So the way we want to think of that, we want to build the third dimension to basically eliminate the potential bias. And in this context, the potential bias can occur from the minimum wage. Treatment group is what? Low wage workers in New Jersey. Control group 1, I have two different control groups. High wage workers in New Jersey. What are the assumptions? The low wage group would have the same trend as high wage group if there were not the new law. Note, the new law affects only for those guys who gets the minimum wage, right? There was nothing in terms of the high wage workers in New Jersey in terms of the policies. Control group 2 would be low wage workers in PA. Recall the example in terms of Maitresh paper. West Bengal, Rajasthan, and then Bangladesh. Here, what? Low wage workers in NG, high wage workers in NG, and then low wage workers in Pennsylvania. And what is the assumption? The low wage group in New Jersey would have the same trend as those in PA if there were not new law, because then they will go in the same path. Law happens, path changes. Clear? Intervention happens, jumps occur. Okay? It does not contain the simple common trend assumption in simple DID. Gruber also has a paper about this in AER, how the mandated maternity benefits affects female wage and employment. Several state governments passed the law that mandated childbirth be covered comprehensively in health insurance plan. And dependent variable was log hourly wage. Independent variable, of course, the mandated maternity benefits law. Method was triple D. DID estimates for treatment group of whom? Women of childbearing age in treatment state versus control state before and after the law change. Then for control group, not in the childbearing age, in treatment versus control before and after. Two already there. And then the last one, DD estimate of the effect of mandated maternity benefits is nothing but difference between 1 and 2. So 1 is my DID, 2 is my another DID, 3 is nothing but the difference between the two DID, and hence it is triple DID. Clear? Fine. That, like the treatment group, women of childbearing age in treatment state versus control state. Now, the female doesn't belong to the childbearing age, and what happens in the treatment versus control? Then you take the difference between the two and you call it nothing but it is the estimate of the mandated maternity benefits on wage. Clear? Fine? Yes.
Just 1 2 minutes
To grab it. Okay. Once you open your eyes, then I'll understand that you have.
We also have other control variables.
They have.
In this paper.
Yes.
Other than
They have.
So I was just understanding when do we use DD, difference in difference, and when do we use difference.
Yeah.
So in DID we have 2 time periods and treatment and control group.
Yeah.
In triple D we have 2 time periods
But 2 different control groups.
but 2 different control groups. So when we have 2 different control groups, we'll use triple D.
Yes.
Thank you.
Or I want to create 2 different control groups.
Or we want to create
Two different
control groups.
Yes. Because think of the minimum wage changes. It has no impact on the high wage workers. It has only impact on the low wage workers.
Sir, in India, we have something 7th pay scale, 6th pay scale. So many in many private universities, some faculty get 7th pay scale, some faculty get 6th pay scale, and there is always dissatisfaction among the assistant professors who are getting 6th pay scale. So I was just assuming if we don't go to 7, but we still continue to work in a similar way. So I was just understanding that way.
we check the
Efficiency. Yes.
Right. Right. Clear? Yes.
How does the triple differencing help reduce the bias in the? Could you explain that?
Because the trend is lot different. I'm assuming now 3 different trends for 3 different group of people. Okay, it's a little bit better than what we could achieve in DID. Okay, triple differencing. I'm going to give you an example. So 2 Indian states, treatment state T and control state C. Clear? So note, program is to boost the TFP by increasing R&D. Okay. If R&D over sales is more than 5%, firms B located in T get a subsidy. Then firms of the treatment state divided in 2 groups. A, who gets the benefit, or A, who doesn't get the benefit, and B, who gets the benefit, right? There are 2 time periods, pre and post implementation of the R&D based subsidy. Counterfactual, what would be counterfactual? Convenient for us to compare A and B within the same treatment state, right? Because this will not be valid if R&D reform has within state spillover from group B to group A. Another option would be what? To compare group B in the treatment state with group B in the control state. Clear? So then this will not be valid if different states have different economic conditions. Okay, so that group B in the treatment state would have treated differently from group B in the control state, irrespective of the R&D. However, we may think of that general economic differences will not affect the relative outcomes of group A and B. Clear? And in that case, we can use the relative difference to estimate what would have happened to the relative outcomes of group A and B in the treatment state in the absence of treatment. Yes?
Could you repeat the last line? I didn't understand.
You can read it. I didn't say anything more than what is being written. Okay? So I'm just creating a lot of counterfactuals, nothing more than that. And creation of these counterfactuals is the art of the DID. The entire thing is how do you create different kind of counterfactuals. Okay, sorry.
I think this is
Sorry.
like you're saying about the art of PID. I think we are like looking at many times into the mathematics or equations of
Yeah.
it. But the beauty, as you're saying, lies in identifying
Yes, the proper counterfactuals.
Because here we are doing it within the state and
Yes.
across the state.
Yes. So one way to think about it, this is what I want to do. Beta 1 T, then beta 2 B, and then you think of it. Beta 3 post program has happened. Then I want to multiply T times B, right? Then I have again the multiplication with the T times the post. I'm just interacting constantly. Then I have the last one where I have the T times B times the post. And all I am doing is a simple assumption that the expectation of my error term conditional on treatment, the state where it has happened and the post is equal to 0. And I successively compute all the expected value. Nothing more than that. And then all I want to do, I want to take the difference of those expected value one by one, right? And that's what my next slide does. So I started identifying my beta 0. What would be my beta 0? The second one minus the first one, right? Or the beta 1, sorry. So beta 0 is being identified. Beta 1 is nothing but the second one minus third one. Sorry, second one minus the first one. What would be my beta 2? Third one minus first one goes like that. But the complication would come when I have beta 0 plus beta 1 plus beta 2 plus beta 4. Still, I can do it because my beta 4, I take the successive ones, and remember your national income or something like that, people used to study double counting. So some of them are pluses and some of them are minuses, simply because I do not want to suffer from the double counting problem. Clear? And you have to just keep a track what you have counted twice and what you subtracted twice. And finally, I would be able to get to my beta 7.
So B here refers to region.
Region, the state. The
So
state.
sometimes it can happen that we don't have a region. We still have two
Possible,
counterfactuals.
possible. That's possible. Not a problem. Not a problem. Not a problem at all. So the way we can think of, instead of 9, that would be the parenthesis, to find out what would be my beta 7. So the triple difference is nothing but, given this equation, is the difference between the two difference in difference. How do I think of? Note the first one is the difference for group B in the first square bracket, right? And the second one is the difference for group A given by the second square bracket. And I then take the difference of the first square bracket and the second square bracket, and hence I can think of it is nothing but the triple differencing. Clear? And the way I can think of it is the indifference for the treatment state by comparing the eligible group B and group A minus the difference in the control state comparing group B and group A. Okay? So I basically have a treatment state where I have two groups, exposed, not exposed. I have a control, two group, B and A, exposed and not exposed. I first calculate the difference in the treatment, then I calculate the difference in the control, then I take the difference in the treatment and in the control, and hence I call it as triple DID. Clear? Right? So given this, the control variables can have, like substantial explanatory power, which would reduce the residual variance, and therefore we may want to think of inclusion of the control variable. Other way to think about the control variable can make the parallel trend assumption needed for identification more credible. Okay? So it basically emphasizes more on the control variable. So these are the identifying assumption, and the assumption basically starts with the parallel trend. Okay? And then it goes in terms of the difference between two difference in differences. It does not need two parallel trend assumption. So it requires basically the outcome of group B and group A in the treatment state to trend in the same way as in the control state if the program doesn't take place. Right? So you should follow the same trend if the program did not take place, irrespective of whether you are in treatment state or in the control state, because the program did not take place. Clear? That's what we have, the identification of the beta 7, and then I just rewrite the beta 7 in a different way. So note, what I have is basically another example. I think, yeah, we have half an hour. So we should finish at 1, no? Yeah. So we have this another example. If I have time, I'll come to that example. Otherwise, I'll go to, otherwise, let me move forward. We can come back later. I'll come back later, as I said. More like, yeah. Let me first do this portion, and then, because you got an exposure already to triple DID or triple difference in or triple D or whatever you call it. So basically, let me start with. So what is the RDD then doing? RDD is nothing but, you can think of this is an alternative. Okay? And the origin of the alternative is something like it is quasi-experimental in nature. And why is it quasi-experimental in nature? Because it used something like a selection criteria. What kind of selection criteria you can think of? Think of, in India, there are different type of poverty line measures, isn't it? Somebody get gas, somebody get sugar and gas, somebody doesn't get anything but still has a ration card. I think there are different colors of ration card available in India. I don't have any one of them. So I don't know that. But I have heard that there are different colors, right? Huh? Yeah, and BPL, some blue, some white, some, I don't know which color, orange, right. So 3 different thing is there, right. So 3 different colors of ration card. You can think of that there is a selection criteria based on the 3 different color. Okay, clear? And I can be closer to one color, or I can cross one color. If I cross the color, I don't get the benefit. If I am delta closer towards it, I still may get it, right? And the delta is nothing but in a probabilistic sense. What I will show you, when there is a cutoff like strict That's like a sharp RDT. When there is a probabilistic kind of delta, then we call it fuzzy RDT. Clear? So that's the main difference between the sharp and the fuzzy design of the RDT program. Okay? Fine? We'll go to that. So RDT, what it does, based on this selection, it again creates two groups, right? A treatment and of course a control group. So the treatment group expected value I'll calculate. I'll compare that with the control group based on that particular selection criteria. Recall, it is not the program being implemented. I have a selection criteria that you would get the benefit of the program. Okay? If you have a blue card, you get the benefit. Or if you are very close to the blue card, you will get the benefit. Right? If you are not 0.5% away from the blue card, then you don't get the benefit. If you are, other way around, you get the benefit. Fine, right? And that's where the role of the Panchayat Pradhan would become very important, right? Because they will clarify whether these guys would be under 0.5 or 0.7 or 0.1 or whatever it is, I don't know. Clear? Fine.
So selection is itself endogenous.
Not necessarily. It could be, but not necessarily it is endogenous. Because I have designed the criteria. I go and I announce this is the criteria, right? So it's something like, it's something like, what should I say? What should I say? Okay, in something like in village in India, there used to be a cycle or bicycle or rickshaw, whatever you call it, rickshaw, where there is a new movie being played in a Maidan, and they would go, oh, movie aaya hai, movie aaya hai, movie aaya hai. Right? Now in movie aaya hai, somebody would sit in front, would pay a certain amount, somebody would sit in the back, pay a certain amount, and who would sit in the front and who would sit in the back would be given by a announced criteria. That's not endogenous. And then that rickshaw got moved away, and then now there is a matador. Right? But the purpose is exactly the same. And you do the sharp RDD or the fuzzy RDD. Right? Yeah? Fine. So RDD was developed mainly to mitigate the selection bias problem.
So here there is no self-selection, meaning
yes, because that is what the purpose of it is. The selection bias. I go, I tell that, this is the criteria. If you qualify, come. If you don't qualify, don't come. Okay? And then it's an experiment. Look at the last one. It is randomized at the cutoff value. And therefore, it can allow for a detailed description of the selection process. Note, randomization at times could be unethical or political, and therefore the DD can suffer from unethical problems sometimes or political problems sometimes, but this design may not suffer from it. Clear? Fine? Fine. I create, just give me 1 second or 3 minutes and then you can ask. Regression discontinuity, I create an example. If you think of India, that's what my sister helped me, who lives in Bilaspur. Because I didn't know how exactly the procedure works now. So for student take IIT JEE, right? And if student scores, what she told me, I hope her information is correct, 90% and above threshold, which is my threshold, they can then appear for what she told is JEE Advanced. Now, on academy, she claims, is a very big one, and physics wala is another big one, right? Which is basically the coaching center. These guys offer a crash course for students scoring 95%, a treatment without any tuition fee. But note, there are people who got 90% has qualified, but also can take physics wala. But people who got 95% and above my threshold would get physics wala without the tuition fee. Clear? So I now want to compare all below the 95% score with all above before and after, and compare students just below the cutoff with those just above it for the JEE advance. That's my RDT. Yeah? And we observe assignment to treatment, and the assignment is nothing but your test score at JEE advance. Realistic example. Do that. Clear? So the threshold is nothing but cutoff. I think it's an interesting exercise. You don't need to know the name of the student, right? You just don't need. You just go there and ask, what has happened? What has happened? What has happened? What has happened? I do think that I do think the physics wala or those on academy or whatever, they are giving some discounts. They must be giving some discount for those guys who got 95% and something like that, or may not be 95, maybe 93. I have no idea. Okay, but this is just like a fictitious, not a fictitious example, kind of real example. Okay. Important concept. Recall my delta. I'm going to give this delta a funny name or a sophisticated name, which is the bandwidth. You remember radio? Bandwidth. You play around with that knob, right? If the bandwidth catches, you get to hear the song. If it does not catch, you don't hear the song. Clear? And that's nothing but my bandwidth. FM 99.8, something like that. Clear? Okay. We might think of assignment of to treatment is random. Strong internal validity, easy to test the assumption, but the drawback is it is nothing but a local treatment effect. Okay. Terminology, sharp RD, assignment is deterministic. Fuzzy RD, probabilistic assignment. Bandwidth, range of comparison. Running variable, which determines the assignment. Threshold, value of the running variable that determines the treatment. Fine? Clear? RCT. Recall what we did. I have Y0, YI1 and XI. Treatment, did I do something wrong? No. Treatment treatment Wi belongs to this set 0 and 1. Wi is independent of Yi0, Yi1 and Xi. We observe them when we observe Yi0 if Wi is equal to 0, and we observe Yi1 when Wi is equal to 1. And that's my treatment effect. We went through it in an RCT context, right? My job would be RCT in a sharp RDD framework. How do I do it? Again, I have this, X is continuous, treatment is same, but note, Wi now takes the value if Xi is greater than X tilde, where the X tilde defines the threshold. Yeah? And then I can think of that Wi I am going to define depending on the threshold, and of course I observe Yi0 and Yi1 in terms of Wi taking the value of 0 or 1, which is being determined whether it crosses Xi crosses the threshold. What is my treatment effect? I am to conduct the treatment effect at the cutoff. What is my cutoff? The cutoff was Xi is equal to X tilde. How does you think of it? Is nothing but recall something like La Hospital rule. Huh? What do we do over there? What did we do? We differentiate, of course, we always differentiate. But why did we apply that? When? Absolutely. You see, limit of x downward moving towards x tilde versus upward moving towards x tilde. We take those two limits, we take the difference between the two, and then we get what we call as lambda ATE. Think of it, the concept of limit in terms of left hand side limit versus the right hand side limit. Here you are thinking of the downward side versus the upward side, and you are taking the difference between the two, and it is nothing but calculates your treatment effect. Given this, sharp and the, what is the difference between sharp and the fuzzy? All you want to do, change the deterministic one to a probabilistic one. You see, I am taking the probability that the treatment to take the value of 1 when x is greater than x star, and it would take the value of 0 when x is less than x star, but both in probabilistic sense. Recall in the previous case, it deterministic, it would take the value of 0, it would take the value of 1. Here it is more like probabilistic sense. Clear? Fine. And that's what I want to think of, the difference between the fuzzy RDD and the sharp RDD. Sharp RDD, look at this diagram. You have expected value of y1 conditional on x and expected value of y0 conditional on x, and this is nothing but x star. Right? So note the two function or the two curve both has the different intercept along with different slopes. And the way I then want to think of calculating the tau x star or tau at the value of x star, which is nothing but the difference between the two, assuming x takes the value of x star. Because when x takes the value of x star, W kicks in, takes the value of 1. Clear? Fine. If x is less than x star, then it is always equal to 0. So I don't need to take into account that. Or, fine. Linear regression, very simple framework. Again, I have the two intercept, two different slope, and I can think of linear regression adjustment plays a key role given the unconfoundedness assumption. And here we are just assuming linear function on both sides of the cutoff. Okay. Left shows two different intercept with two different slopes, and therefore we are estimating nothing but the difference in the intercept, difference in the slope coefficient times my controls, which is x star. The way we then want to think of the term is what we do not a little bit different in terms of local linear regression. Why it is local linear regression? Simply because I am going to fit the data which is sufficiently close to the cutoff. I don't care about the other data. I'm going to care about the data which is sufficiently close to my cutoff, and how sufficiently close I am going to consider them, that depends on my radio frequency, which is nothing but my bandwidth. Okay, so I'm going to conduct, this is my universe, I'm going to conduct the local linear regression, nothing but in a subset of the universe. The subset is nothing but concentric circle. The concentric circle would be determined by the frequency of the radios, which is nothing but my bandwidth. Right? Clear? Fine. Recall the concentric circle has one advantage. They have the same origin. Clear? Fine. So given this is how do you choose the age, and there would be a trade-off again between bias and variance when the linear function are viewed as approximation. So one way you can think about, as age decreases, we use less data around the cutoff and vice versa. Clear? So with more age, your circle expands. If you use all big age, then you are actually using the entire circle. So whether how much do you want to shrink the circle depends on bandwidth. Shrinkage then determines the number of observation. Smaller bandwidth leads to small data set. Larger bandwidth leads to larger data set. And hence what you should do, change the bandwidth and see whether how does the result varies. Clear? Fine. And that's your robustness in R&D.
But if we, like, how do we interpret, whether we keep the bandwidth smaller vis-a-vis when we keep it larger?
Yeah, the result should be same. So
That should be same.
Yeah.
Suppose we are saying that bandwidth is increasing, that means we are giving more leeway for that cutoff.
we are using more data around the cutoff. It's not we are giving more leeway in that way. So this is the cutoff. If your bandwidth is increasing, you are using more data. If the bandwidth is decreasing, then you are using less
But
data.
that bandwidth is basically a point for us to establish the discontinuity.
Yes. Yeah. No, the bandwidth is not. Discontinuity is given by X star. You have X star minus H, X star plus H. If H is very small, then your observation are around X star. So you have less observation.
But if we increase that
H, then you are going, so then you are spreading the line. So this is my line. This is my X star. This is plus H or minus H, this is plus H. So whether you use the entire line, that means you are using the entire data set.
But it is not only about the data set, it is also about, suppose we increase this bandwidth,
Yeah.
right? Then
Yeah.
that means
Yeah.
Where the X star was happening,
Yeah.
that means the results are basically same before and after in that. Will that not be the case?
So this is my line. This is X star. This is my X star minus H. This is my X star plus H.
And we are looking at the difference.
We are looking at this portion of the line running from X minus to X plus.
But there is another line also from where we are looking at it.
No, I'm just thinking of the bandwidth now. How much data I should use? If I move the H, I can come here. If I decrease the H, I can come here.
This is clear, but then suppose if we go to those curves which you showed earlier,
Yeah, because I'm already approximating those curves by the linear function.
by the linear function.
Yeah.
If we increase the band, can we have a look at this bit? Suppose we are going with the linear one, this one.
Yeah,
So if we increase the bandwidth
Yeah.
and the results remains the same,
yeah.
then the difference between the two is not increasing, it is the constant one in that case.
No, but you are looking at the difference in the slope coefficient.
That's what I'm saying. That means if it doesn't change with the bandwidth,
Yeah.
that means they are not as different. They must be
No,
different
no,
in
they are
that.
not as different. That's okay. That's okay. But at the end of the day, I'm going to claim that this effect is same irrespective of the choice on bandwidth. That's all I'm going to claim.
That point is clear to me. That
Yeah.
we are using it for kind
Yeah,
of robustness. as
yeah,
well.
yeah.
But my only point was that if we are increasing the bandwidth, then the difference between these
No, but in this diagram, think of this is the portion where is your X star. So whether given this is your X star, you can have from here up to here. You can have here to here. Does not matter. It does not matter. Whether you take this data until this or whether you take this data until this, these two curves exactly remains the same. They don't change their position, right?
difference between them. That
Yeah, but that's the difference between the term is nothing but by the slope. How does it matter? It would not matter at all. I don't think it would matter. Yeah? Okay. So given this, I just did the formulation. So note what I do. This perhaps would make your point very clear. So I have a left hand side, X star minus H, where Xi, the observation, belongs to X star minus H up to X star. Here it belongs to X star up to X star plus H. I do a minimization on my left hand side. I do a minimization on my right hand side. If I am interested in alpha L and alpha R, I get alpha L hat from here, I get alpha R hat from here, I take the two difference, and that's nothing but my lambda hat ATE. Clear? Fine? Left hand side, right hand side. I do two different minimization. It's something like a V function, which becomes discontinuous, right, at x is equal to 0. So you do the downward portion, you do the upward portion. You have the slope, you have the intercept. Clear? You take the two intercepts and take the difference. Why the intercept? Because that is like my sharp jump of at x star. Okay? Fine. So given this, yes.
Like one reason to choose a smaller bandwidth would be that the linear fit
Better approximates.
and the reason to choose a larger edge would be more data.
More data.
So there's a
So that's your bias and variance trade-off, right? You remember we went, I think I said somewhere, bias and variance. Clear? Because at the end of the day, I mean, Taylor exists. So it is basically the Taylor series expansion, and you are ignoring the higher order terms. So it is x1 minus x0, and then factorial 2 times x1 minus x0 square, factorial 3x. You are just eliminating that and just taking the approximation ends at the second order. Okay, and then you are linearize this in terms of your x star. And when you linearize that in terms of x star, that is where you get that. Clear? Fine. RDD. RDD. Okay. What happens? Why are you coming here now? Why? Why do you want to take the laptop? Huh? Yeah. That's good. Which one? G? Yes, G. RDD.2. Let me run this program. Fine? Let's do it. This is all I am doing. Right? I feed this line, I feed this line. At 5, the jump has occurred. And if you look at it, where is the window? There. This command is not there. So just install it. It would take maybe 1 minute. What's the time? 12:54. Huh? Complete? That's good. So let's think of a little bit. One program I'll go through line by line. Then the next two I'll leave it to God's grace. Okay? And God will take care of it, hopefully. Clear all means I don't care, whatever is there. So then I have seed 1, 2, 3, 4 because I want to keep the same results always, hopefully. Observation 100, I get an x from an uniform distribution 0 to 20. Lower limit, upper limit. I create a treatment if x takes the value of 5 and above. Recall my x star. Y0 I create as 2 plus 0.5 times x. Y1 is nothing but Y0 plus 3, right? Intercept difference, right? And then Y is nothing but Y0, which is this guy, plus 3 times treatment, plus a random error term, normal with 0, standard normal rather than. I define my cutoff at C is equal to 5, and I select my bandwidth at H is equal to 1. I center the running variable around the cutoff. So whatever I have X, I take the centering X minus C, which is in my case as 5. I then create an indicator for observation within bandwidth, and then I basically run separate left and right hand side of the cutoff. Recall? Minimization exercise, that's what we are doing, right? And this is the left side and that's the right side. I do the local linear regression on the left hand side. Was it clear? Right? It's like slide and the stator should go together if your logic is correct. Okay? So this is my left hand side, if left, and then I get my alpha L and my beta L also. Right hand side, I get my alpha R and my beta R. I display should be alpha R minus alpha L. And then I plot them. That's all I do. What I do is basically, this is a built-in command, right, of RD robust in stata. I use that, and then I want to see whether it matches the result or not. It would never match the result simply because it computes robust standard error, corrects for heteroscedasticity, finite sample bias, selecting optimal bandwidth by their different way. Okay, clear? And even with different bandwidths on each side. And that's why the written program and the status, what should I say, inbuilt one would not match, right? Then it is using a kernel function which is triangular by default. So observation reaches point closer to cutoff, get more weight if you have triangular. However, with regress, there is no kernel weight. So treating all observation, treating all points within the bandwidth exactly in the same way. I put equal weight, and the weight would be 1 over n in this case. Can I match the result with my written program with status built in? Of course I do. And this is the way to do it. Right? Clear? And that's what I want you to do slowly at the end of the day. Right? So note, if I run this program now, that's fine. So let's look whether my claim is correct or not. 2.66009999 whatever value, and then I have used the RD robust. It's 2.6601. Clear? So I understand the theory, I understand the stata. Stata understanding is useless actually. Fine? I'll just, so given this, what you can do, I think, shall I close it please? It is given to them. You all have that same file. I don't want to change it. And then this fuzzy is for the fuzzy RDD design, and I want to go back to my PowerPoint and wrap up. How do I wrap up? The way I then want to think of, this is like the probabilistic sense. So I want to think of jump in yi at C star, jump in yi at wi at x star, and basically it is nothing but an world-based estimator. Look at the stata do file. It is very clearly step by step telling you what to do and what not to do. Ulrich control function. So here what Ulrich does, you can think of this RDD is nothing but an endogenous switching model or a threshold kind of regression. Someone was asking me yesterday, I forgot, I don't see him here now. Yeah, you. That is the threshold model. How do you do it? So all I do is create an indicator variable. If the indicator, if certain variable takes the value higher than, the indicator takes the value of 1 and then otherwise it is 0. Right? I combine them and I run the regression. What does it mean? It is a switching regression model. But here what we do, it's an endogenous switching regression model. So I can think of that given it is endogenous switching model, I use or I can do something like a control function estimated. How do I do it? I want to consider linear models for the potential outcomes. One outcome is y0, no treatment, y1 with treatment. Clear? Then I want to think of y is nothing but equal to mu0 plus my treatment with the binary indicator, x minus mu x times beta 0 plus w indicator, x minus mu x times delta. Then my u0, recall I have that in the beginning event, and then w times u1 minus u0. That also I had in the beginning. So our question is, I want to estimate the average treatment effect, delta, as well as the average treatment effect of the treated. Right? Clear? So that's my goal, given the instrument for W. What I can do, first, I can think of that any function of x, y is uncorrelated with u0 and u1. So we can then apply instrumental variable on what? On the last equation of these slides. How do I do it? That's the most important one. The first I want to think of that expected value of W times the difference in the error conditional on what? The x and the other variable z is nothing but equal to some constant, which is eta. Okay. I want to use something like IV to consistently estimate all the parameter except the intercept. I cannot estimate the, I don't want to do in terms of the intercept. So note a sufficient condition here that there exists no unobserved heterogeneity in the treatment effect. So I have eta 0, tau wi, xi beta 0, wi times xi minus x bar times delta plus an error term ei. What does a control function does here? It's a method which relies on expected value of y conditional on wx and the set of other explanatory variables, which is my z. And then it uses something like an OLS where we write the rewrite the endogenous switching model. Why it is endogenous switching model? You see that this is one part of it. And this multiplied by the W, this multiplied by the W is the other part of it. When W is equal to 0, this goes away. This, you don't have that. When W is equal to 1, then only you have it. So when W is equal to 0, you have alpha 0 plus x beta 0. When W is equal, forget this term. When W is equal to 1, you have tau plus x minus mu x times delta. Clear? We can do lot of things here, add a probit, propensity score, whatever, we'll come to that. We can arrive something like an estimated equation, which I am going to call like this. What is GE? G is nothing but my what I call as generalized error. Okay, so it is a little different than the normal error, and hence this is like my generalized error, which has a coefficient of gamma 0, then it has theta w, and again another generalized error. Because this generalized error is u1 minus u0, this generalized error is u0. Clear? Simple way to think about. To estimate the ATT, first we make a regression of yi on 1, xi and gri using wi is equal to 0, no program. Then I obtain y1 hat for each I. we then get two different set of fitted value to form the treatment effect for each, and then I take the average across the subsamples. So one subsample, remember, treated, one subsample, remember, they are not being treated. And I basically obtain an estimate on the untreated also in this particular way. So this is the way the ATT works here. I believe this is some results from Ulrich. I'll show you how exactly to do it in Stata. I think that would make a lot clear the way it works. Where is the Stata? Yeah? Should be there, no? Where is Stata? Well, it should be here also, no? No, this is 15. Okay. So note, let me go through this even if I take 5-10 minutes extra. Every day I am taking some time extra, sorry. That I don't know. So, seed, number of observation. Covariates, x1 normal, x2 normal. I need two instruments. Remember my sample selection problem? Z1 and Z2, exclusion restriction. Selection equation, eta or normal, I create W star, my indicator. Okay? In terms of x1, x2, and exogenous or something like exclusion restriction. I then, as soon as I get W star, I create my W, which greater than W star, which is equal to W star and greater than 0. What I do then, I error terms of for outcome correlated with eta. Because remember sample selection problem? Bivariate and the covariance is not equal to 0. So we do generate U0, U1, Y0, and Y1. My observed outcome is nothing but weighted average of W with Y1 and Y0. Recall 1 minus Xi, Yi0 plus Yi, Xi, exactly the same thing over here. Selection equation and inverse Mills ratio, run the probit on treatment with x1, x2, z1, z2, all the variable, exclusion restriction, z1, z2, get predict the linear prediction, get the inverse Mills ratio. You see the inverse Mills ratio in two ways, IMR 1 and IMR 0. Why? 1 would be W is equal to 1, 1 would be W is equal to 0. So given this, I run the regression of Y on X1 and X2 and IMR 1 for my sample selection when W is equal to 1, my treatment. I write them as matrix, the coefficient and the variance covariance matrix. I now run with IMR 0 for W is equal to 0. I then get a second set of coefficient. I then basically do a summary statistics of x1 and x2. I get the scalar of mean of x1 and x2, and then all I want to do is the sum of the IMR when W is equal to 1 and W is equal to 0 and create two different mean belonging to IMR 1 and IMR 2. And then I can compute the average treatment effect on the treated, untreated, and total one. Clear? Recall our main interest lies with ATT, the average treatment effect on the treated. And I display those three results. I hope it would run. Shouldn't be any problem. Done. Done. Let's go for lunch. I have to go. बताइए.
Just I'm recapping.
Yeah.
So we use DID when we don't have any. When it comes to difference between treatment and control, there is no bandwidth or threshold level. They are two separate groups. In then we use DID, and when do we use regression discontinuity? When there is threshold level of some
No, not yet.
difference.
I one way to think about it that I want to make a distinction. How close are you given your selection criteria? I want to use R.
When we have some criteria. When we don't have any criteria,
If the policy is completely exogenous, I go back and I do the DI.
like looking at the example about the training.
Yeah.
So the people who got training, people who don't got training, there is no threshold bandwidth
Absolutely,
level.
but still there could be. I'm going to give you the training if
If
you are loyal to me.
If there is some,
If and the loyalty I'm going to measure by the number of years you have worked for me. If you have worked for 15 years 1 month, you will get the training. People who are sufficiently close to for 15 years 1 month get the training, and then the others don't get the training. That's my creation of that one. That's my creation of the thing.
so many times when we do impact evaluation study for suppose CSR programs,
Yeah.
many companies implement CSR program. So then we should understand how does company selects beneficiaries, how does company,
Yes,
well, that is very crucial.
very crucial.
Then we design our
Very
plan of analysis or plan of data collection.
You are absolutely right. Yeah.
It was very heavy. There were many things covered: RDD, DIDD, then endogenous switching. Which textbook we can go back and Woolrich econometrics of cross sectional,
Woolrich. Then there is a fantastic book by Andrews,
mostly harmless econometrics. Woolrich has econometrics of cross section and panel data
That's a
also.
little bit higher. I follow some portion there. But introductory econometrics is very loosey.
It covers these
It
concepts.
covers everything.
Thank you, sir.
And in Woolrich,
We do in the next after lunch.
you have to present, come and show me your output.
Yes, yes, it's 2:30. I'm just announcing.